All right, everybody, thank you for joining us today. My name is Jim DePalma from Wales-Darby, and today's topic is going to be understanding low voltage wiring. Our goal today is to make sure everybody understands the sequence of operation in a standard HVAC system via the low voltage side. How are we going to turn the system on? How are we going to turn the system off? How are we going to control our pumps, zone valves, fan motors, what have you? That is our goal today, and just hang on and enjoy the show. Let's go. Okay, so to get things started, we need to understand how we make up a circuit. And it's very simple. It may look complicated. Gosh, there's a lot of wires there, parts and pieces, but we really need three things. We need three things for every circuit. These must be here. You can't have a circuit without it. So we have to start off with power. Kind of obvious. And since we're going to concentrate on the low voltage side, that power is a transformer. Next thing is we're going to need a switch. What's going to turn our system on? What's going to turn our system off? And the most common switch is a thermostat. All right, it's an automatic switch. And then what's going to happen next? Well, I've got my power, I've got my switch. I have to energize something, and we're going to energize a load. And the most common load we're going to see in a heating system, hydronic heating system, would be a zone valve motor. But your circulators are also loads, okay? And fan motors are loads and things of that nature. So we need these three things in every single circuit. You will have multiple switches in a circuit, and you'll have multiple loads. But we always have to have these three things in every circuit: power, switch, and load. This is the most important item of today's presentation, bar none. Power, switch, and load, power, switch, and load. So I want you to think of this as a triangle. All right, power is on top, my switch is to the right, and then the load's to the left. And when the switch is in the closed position, we have completed the circuit. Power will now flow from the power source through the switch to the load back to the power source. That's a completed circuit. If it's a open switch, now we break the power going to the load. So closed switch, we complete the circuit. Open switch, we break the circuit. Now, where are we getting our power from? We're getting our power from the transformer. The transformer is going to take line voltage and either step it up or step it down. So we're going to be concentrating more on the step down side of the business today. And the way it does it via magnetism. And our transformers are rated in VA. And the most common VA you're going to deal with is the 40 VA transformer. And that will take 120 volts and step it down to 24 volts. And it's going to do it via magnetism. We have a primary side. We have primary windings on one side of this iron core that's in that transformer. And then we have the secondary side where we have less amount of windings. And it's a 5-to-1 ratio. And that equates to the then becoming 24 volts. Our switches are in our systems. We have multiple types of switches. And what do? Well, switches are going to do what? They're going to turn things on. They're going to turn things off. That's basically what a switch is going to do. Now, how do we identify our switches in our systems? Well, two of the most important symbols you're going to see is NO and NC. NO means normally open. That means the switch is set up in a normally open position with no power applied. So I'm going to pull up my laser pointer. So right here, NO, normally open. So that symbol there is telling you that switch is in a normally open position. And then when we apply power, it'll close. Down here, NC means normally closed. That switch comes from the factory closed, and when power is applied, will open. So if I want to turn something on and off in an intermittent fashion, it'll be wired to a normally open switch. Then this way I can close it when I need to. If I need to power something consistently and break it occasionally, it'll probably be powered to a normally closed switch. Now, the switches that we're going to be playing with 99% of the time in our systems are single pole, single throw, or double pole, double throw. Let me give you a visual of what that means. A single pole, single throw, think about that I have a fishing rod in my hand, and at the end of my line I have a ball. And I have you standing in front of me, and I cast the ball to you, you catch it. Single pole, single throw. We're just moving one switch. We get good, and I'm holding a fishing line in both hands, and I cast both of them at the same time toward you. You catch both balls at the same time. That's a double pole, double throw switch. So here's an example of what it would look like if it's in an ice cube relay. So you can see both switches are set to normally closed. So there's power at that switch right now. And if we, there's no power. And if we apply power, they're going to change their position to normally open. We just turned something off. Okay? So here's a picture of that ice cube relay. And right down here, where the green arrow is pointing, that is a load. That's a hunk of iron, and we wrap copper wire around it. And if I energize that copper wire, I make a magnet. And then right up here, you could see our switches. So right here, the switch is in a normally closed position. We energize this copper wire, we make a magnet. Now the normally closed is going to open, and the normally open right here is going to close. You hear that clap that you hear out in the field, and maybe the gentleman you're working with that day tells you, hey, kid, that's the relay pulling in. Well, that's the switch changing positions, okay? And that's a double pole, double throw. So now switches, they turn things on, they turn things off. So we have all types of switches in our systems, thermostats, aquastats, they're switches. Other switches that we can have in our systems are low water cutoffs. They're normally closed switches. Every zone valve has an item in it called an end switch. And when we close the end switch, we start the next series of power, switch, and load. These little actuators that you normally see on radiant manifolds are generally 4-wire, and they have an end switch. So when they open, they close their switch. And again, we turn on the next series of power, switch, and load. Now, switches that control temperature are designed to open and close on either temperature rise or fall, as you can see. So that's our heating stats, okay? High limits and aquastats. And what does that look like on a wiring diagram? Well, up here is your normally open, right here is your normally closed. Here's another example of a switch, and that may indicate in a wiring diagram a pressure switch. Sometimes that's used to identify a pressure switch. This one right here, this very odd looking one, is a thermostat. And I like to kid with people to say, hey, that looks like Picasso, the artist Picasso in the cubic period. All right, that's women sitting on a bench. I do that on purpose so you can get that visual in your mind so you don't forget it. So if I can find this on a wiring diagram, okay, that's my starting switch. That's the switch that's going to start the system. Down here is a symbol of another important switch. It's a fuse. And it's a one-time switch, as you can see. And if you're thinking ahead, well, that means that fuse is a normally closed switch. And if that switch opens, we've blown the fuse. So yeah, we can change the fuse. It's back to completing the circuit. But gentlemen, we do have to figure out why that fuse opened. So these are the most common switch symbols you will see. Now loads. Loads are going to use power to do work. So motors, coils are loads. So I have my motors in my 4-wire zone valves, a heat motor that you see here in the Tekmore 571. That's a heat motor. We're going to energize a copper coil that's going to heat up a wax pill. So that's a heat motor. So it's a slow opening motor. A lot of these actuators are heat motors. And then we have our circulators and fan motors. Those are 120 volt motors. But then this load right here, that relay coil, that's a really important load because that's the load that's going to have switches assigned to it. and that will turn things on and off in both the low voltage and line voltage side. So what does that load look like? Or what does it look like as a symbol? So typically you'll see things like this, but the relay coil is this symbol right here. This is the coil, or this is the symbol you really want to focus on, because again, if I can find that on my wiring diagram, and it'll be addressed with a letter and a number, it could be C1 or K1 or whatever, it will have switches addressed to it. And that will tell you what it's going to turn on and off on both the line voltage and low voltage side. So now we know our parts and pieces, power, switch, and load. Now we can start building circuits. And when we build our circuits, they're built in either what we call series or parallel. And they're both used in our HVAC circuits. Your loads are never in series. They're never wired one after the other. But your switches usually are wired in series. So series means I'm stringing things together in a row. So if you think pre-1990 Christmas lights, those were lights wired in series, meaning if I lost one of the lights burnt out, the whole string of lights went down. Now they're wired in parallel, and if I lose one light, I don't lose the whole string of Christmas lights. So let's now start equating this to what we're going to start seeing in the boiler room. So here's my system, and the dark drawn line with the arrowhead, that signifies line voltage, and it's labeled L1, L2. So there's my power. Next I need a switch. Well, I have a service switch, so let's think of that as the switch at the top of the stairs before you go into the basement, and that's in a normally closed position. Then I got a safety low water cutoff. That's my safety at the boiler itself, and that's normally closed position. The probe is surrounded by water, and as long as the probe is surrounded by water, we keep that switch closed. And then we have our T-stat, which is our switch that'll automatically open or closed. And then when we go down to where the burner is, that's our load. So I got my three things. I've got my power, but I've got switch, 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 and I've got a load. How do I energize that burner? Well, we have to close the thermostat, and the service switch and the low water cutoff switches have to stay in the normally closed position. If either one of them open and the thermostat is closed, we've broken the circuit. We will not energize the burner. Okay? So if your low water cutoff has got a dirty probe and it can't receive the electrical signal back into the probe through the water, it's now open, and our system, our boiler will not run. There's a good example of a switch that's now changed its position and turned off our system. All right, so going further into the boiler room, here we're looking at a single zone circuit. So there's the transformer, there's my power. What's my switch? It's my thermostat. And what's my load? It's a zone valve motor. So I've completed it, power, switch, and load. Thermostat closes, I energize the zone valve motor, thermostat opens, now we cut power to the zone valve motor. That's a single zone. Now if I make it a two-zone circuit, each circuit is going to share the same power from the transformer. So I got power, switch, and load for zone 1, I've got power, switch, and load for zone 2. If this zone valve motor fails, it doesn't affect this zone here. If that thermostat closes, I'll still energize that zone valve. If we reverse it and this zone valve motor failed, it won't affect this side either. So these two zones are wired in parallel. We are sharing the same power source, but each circuit still has its own switch and load. Now we make it 3 zones. All right, this is stuff you normally see. This isn't anything new. But now at this point, if I'm going to put a 4th zone in or a 5th zone in, getting all those wires to connect at the transformer, that's going to be tricky because now there's just not enough room to get all those wires underneath the screw to make a good connection. So what's the next thing you see in the boiler room? You start seeing wire nuts. So what did we do here? We took each side of the thermostats, wire nutted them together, and then took another piece of wire, single wire, to our power source. We took one side of each zone valve motor, wired them together, and then took one wire to the other side of the power source, and we've completed the circuit. So what you see right here is no different than what you see right here. We just now cleaned up the wiring by using a wire nut. And to electricity, it doesn't matter. When we use a wire nut and we put wires together, it just looks at that as straight wire. So when you see the wire nuts, that's what's being done. So you want to make sure that when you are wiring up a system, or maybe if you have a system that's having problems, check and see that you've got the right wire nut or the right wire nut was used, because you may not just have a good connection. And once you do screw that wire nut on, twist it on, and make a good connection, you want to tape it off so even if somebody tugs on the wire by accident, it doesn't pull it out of the wire nut. So this is right out of Honeywell's manual, and this is a 4-zone valve wiring schematic. So the way they draw it up here, when you see those dots on any of the wires, that represents a wire nut. So over here we've got our darkly drawn lines. That is line voltage. So there's our line voltage coming into our transformer, pardon me. And then we have 2 dots on the line voltage that shows you wire nuts, and we're bringing that line voltage down to the aquastat relay on the boiler. Then over here on the lightly drawn lines, that represents low voltage wiring, and there's our thermostats. And the way they drew it in such a way that you can see each individual wire going to the thermostat. But in reality, this wire here, this wire here, and this wire here are wire nutted right in this spot. And then the wire that's coming from each zone valve motor, this one here, this one here, this one here, they're wired together at that wire nut. And then down here, and these would be your yellow wires here, gents. And then down here, your 2 reds, the end switch, well, one side of each end switch is ganged up together to this wire nut. The other side of each end switch is ganged up together to this wire nut. And then we take one wire and one wire down to T and T on the boiler aquastat relay. Now, there are different style zone valves out there, and we have either 4-wire zone valves or 3-terminal zone valves. And that's the Tekmore 571. So we're going to solve a great mystery here. It's a 3-terminal valve, but in actuality, it's still 4 wires. So that standard zone valve that you're probably familiar with, the Honeywell's got 2 yellow, 2 red. 2 yellow is the motor, 2 red is the end switch. Well, on the Tekmore, 1 and 2 terminal is the motor, and 2 and 3 terminal is the end switch. Now, how can that be? Well, it's a heat motor valve. So what happens is we have a wax pill, and we've surrounded it, or we've wrapped it with copper wire. And when we energize the copper wire, it creates heat, it heats up the wax expands, it pushes down a plunger, which is going to open the valve. And on one side of that plunger is half a switch. At the bottom, when it completely opens the valve, is the other half of the switch, and when the 2 sides meet, we've now closed the end switch. That also means we've broken the connection at terminals 1 and 2. But since it's a heat motor, it's a slow open and slow close. Once it's fully open, it's going to very slowly start to close. And if the call for heat is really long, it'll start to close, and as it does, then we start to re-energize 1 and 2 again, and then push it back more to open. So 1 and 2 is the motor, 2 and 3 is the end switch. We call number 2 a common terminal. And they're wired in parallel. They're both sharing the same power source. Now, this is important when it comes to amp draw. I got to make sure that I have the proper size transformer for the amount of power that I need for the amount of zone valve motors that I have. So you have to look up the amp rating for each zone valve motor. How much power do they need? So if we have too much draw on that transformer, we're going to smoke it. We're going to burn it out. So if you look this up, you can even Google it at any time. Here I Googled Honeywell 4-wire, and it's a 0.32 amp draw. The Tekmore 571, the 3-wire or 3-terminal, is a 0.9 amp draw. Tekmore Zone Sentry, this is our 4-wire motorized zone valve, is a 0.06 amp draw, lowest amp draw on the market. So one of the neat things about our industry is we do have formulas so you can figure things out like this. And this is a very simple formula. The amount of amp draw times the number of valves times 24 volts equals your volt amps. So let's put it into practice. So if I take that 0.32 times 4, I get 1.28. Times 24, I get 30.72 volt amps. So for these Honeywells on a 40 VA transformer for a 4-zone system will work. You math it out to 5 and you'll be just under 40 VA. So that would basically work, all right? If you take the Tekmore 571 at a 0.9 on our box, it says times 3, you get 2.7 times 24, you get 64.8 volt amps. So by math, that's way too much for a 40 VA transformer. If all zones called at the same time, we have the potential for burning out that 40 VA transformer. That happening is there's a chance that could happen, but most likely that wouldn't happen. And the way the valves operate, it would kind of stagger that amp draw. But in reality, you really should have a 75 VA transformer here. The Tekmore zone century to 0.06 times 12, equals 0.72 times 24. That's 17.28 volt amps. That's the lowest amp draw on the market. That's 12 on a 40. You could double that and you'd still be below the amp draw of a 40 VA transformer. And the way that valve operates, the body of it is a ball valve. There's no flapper, it's a ball valve. And in the motor, we have a circuit board. So since it's a ball valve, it's a quarter turn valve. So when there's a call, we energize the valve and open it, quarter turn, and then we cut power once it's open. And on that circuit board, there is a capacitor, and the capacitor is storing power. So it's keeping the board energized. The board is recognizing or monitoring the call for heat. And then once the call for heat is satisfied, then we power and close the valve. So it's not a constant energy pull to keep the valve open. I'm not fighting a spring to keep it open like Honeywell. So because of that, we only power open when needed and power close when needed. We're not pulling constant power the whole time. 0.06 amp draw, lowest VA on the market. All right, so if our load is going to be higher than a 40, we need to go with a larger transformer. Now, circulator relays. Circulator relays, or relays in general, they're the bridge between line voltage and low voltage. And here we're showing you the Tekmore SR501, which is our equivalent to a Honeywell 832, 845, and an 89A. So what's happening inside this? Well, right over here is our transformer. And these darkly drawn lines with the arrowheads coming in at N and H, that's our line voltage. So this is the primary side of the transformer. Over here is the secondary side. So this is the 24 volt side. And if you follow the wires out to here, to TT or RW, what do we have right over here? We have our thermostat. Okay? And so there's our switch. We follow it down, and then right here, this represents a hunk of iron with copper wire wrapped around it, and that is our load. And we follow the wire back, we've completed our circuit. We've got power, we've got switch, we've got load. Now, you can see a jumper from H to number 3, terminal 3. So that's bringing power to terminal 3. And as we go up here, you can see a normally open switch, and that's terminal number 4. And if we continue up, you see a normally closed switch, and that's terminal number 4 NC. So that means right now, terminal number 4 of NO is not powered, but number 4 NC is powered. Over here, we have dry contacts. Number 6 is normally closed. Number 6 over here is normally open. This is going to be a double pole, double throw. So what's going to happen is when our thermostat calls, when the air temperature changes, come on now, Mr. Thermostat, do your thing. So when the thermostat calls, and right now we're not advancing. Hang on, please. I hate these technical difficulties. Things like this happen, guys. All right, so now air temperature changed, thermostat closed. Watch what happens to our switches. All right, so now our normally closed switch is going to open. Our normally open switch is going to close. We now have sending power to normally open terminal number 4. Circulator comes on. We also now close terminal number normally open 6, and we make a fire. So why did we wire the circulator to number 4 and O? Because I want to have intermittent operation. I only want the circulator to run when there's a call for heat. If I wanted the circulator to run at all times, I would have it on normally closed terminal number 4. Okay? So if you were doing something with a non-electric zone valve system and you need constant circulation, maybe a panel rad system with constant circulation, non-electric zone valves, you'd wire that circulator to terminal number 4 and C. All right? All right, so the PowerPoint is just going to do the same thing over again, so you just get to watch it again, and there we go. All right, so in our wiring diagrams, relay coils are going to be labeled, and they will label the switches that are addressed to them also. So what are we looking at here? Well, you see the L1, L2, darkly drawn lines with the arrowheads. That's your 120 volts. And the way it's drawn is anything that's on the line voltage side is drawn above, and anything on the low voltage side is drawn below. Low voltage wiring is either dotted lines or lightly colored lines. But the L1, L2 that you see on both drawings is the same power. So what's the difference? There's my transformer. So if I look here on the low voltage side first, here's my power, there's my switch with my thermostat, and I've got a relay coil. You've seen that before, and it's labeled as 1K. So that's important because now I can look on the line voltage side and see another switch labeled 1K1. So in order to turn on or energize this load, as long as the thermostat is closed, I've completed my circuit here of power, switch, and load. And now when I energize relay coil 1K, 1K1 switch closes, and now I energize that load. Here's another drawing to represent the same thing. You can see my incoming power, the L1, L2, which is the same on both sides here. There's my transformer, which is stepping down. Well, what's my switch? There's my thermostat. What's my load? A 1K relay. So here's my power, switch, and load. Then on the line voltage side, I see two switches, 1K1, 1K2, and I see 1, 2, 3 loads. So how is this going to work? Well, if we close this thermostat and energize 1K, complete this circuit, now I'm going to close 1K1, 1K2, and I'm going to energize heat strip 1, heat strip 2, and turn on the fan motor. If you're really paying attention, this is wired in parallel. This is important because let's say I lose heat strip 1. It burns up. It's not going to affect heat strip 2, and it's not going to affect the fan motor. Let's say I lose heat strip number 2. Well, it's not going to affect heat strip 1 nor the fan motor. What if I lose the fan motor? I'll still energize heat strip 1 and heat strip 2, but in reality, they'll end up burning up because we can't dissipate the heat off of them. So if you run into a job and you have some heat strips in ductwork and they're not working, go check and see if the fan motor is working, because if that failed, that's what ended up burning up your heat strips. So again, these are wired in parallel. Now here's the same diagram in a ladder diagram. And I love ladder diagrams because ladder diagrams to me are much clearer, and you could see the sequence of operation clearer. And why do we call it a ladder diagram? Because gentlemen, these are rungs. So across each rung, I can have as many switches as I need, and if there's going to be multiple loads, they could be there too. Again, dark drawn lines with arrowheads are line voltage, lightly drawn lines are low voltage. In between, the transformer. So how do we energize this system? No different than what you just saw. There's my normally drawn open thermostat, so we close the thermostat, energize the 1K relay, complete the circuit. Once 1K is energized, 1K1 switch closes, 1K1 switch closes, 1K2 switch closes. We energize a fan motor and both heat strips. So now we're looking at an Honeywell L8148E, something you guys play with all the time. And on top, it's showing you where different items would be wired to this relay. So you can see where T and TV, that's where the thermostat would be wired. Then you see this W and Z, and that's another place where you can wire another control, a low limit. Then you also see B and R, that's the high limit. C1, C2, that's where a circulator would be wired. L1, L2, well, that's your incoming power. And B1, B2, that's where the gas valve would be located. But it doesn't tell you the sequence of operation. Let's look at the bottom drawing. The bottom drawing is going to show you the sequence. So what do I mean? Well, here's my incoming power, L1, L2. There is my transformer. Look at the low voltage side first. So here's power. Well, what's my switch? Well, if I go across here, here's T and TV. That's where the thermostat would be. So let's use our imagination. Let's put a jumper here across these two terminals. So here's my power, here's my switch. What's my load? 1K. What is this here, this jumper Z and W? Well, these are two terminals, and it gives you the opportunity to put your low limit there if you choose. And if you don't, it comes with this jumper between the two terminals. Well, those are two, think of them as wire nuts. And you just have a piece of wire between the two wire nuts. So here's my power, my switch, my load. I complete the circuit. I've energized 1K. Find the switches associated with 1K relay. Well, on the line voltage side, here's 1K1. So that switch is going to close. And now what's wired at C1, C2? Circulator. So the circulator is going to come on. Then there's a 1K2 switch, and that's on the low voltage side. So as I go through that switch, here's my B and R, and that's a normally closed switch. Well, that's the high limit. That's a safety switch. That switch has to stay closed. And that's a temperature switch. So as long as the temperature is not above the high limit setting, that switch will stay closed, and we'll come to terminals B1, B2, which is our gas valve. So now we would then open the gas valve, and we would fire the boiler. Here's another example of a ladder diagram, and this one's really pretty cool because I'm going to have 3 zones of space heating and a zone of domestic hot water. This is going to show you what domestic priority actually is. So on the top, L1, L2, darkly drawn lines, that is our line voltage side. And for each rung, you could see a switch, a normally open switch, and you could see a load, which is the circulator. You see the legend on the other side of this drawing. Then on the bottom, there's our transformer, lightly drawn lines, and then you can see again our switches, which are identified as room thermostat, and then we also have an aquastat. So one thing to remember, if you see stat in a word, that's a switch. So we have an aquastat as a switch and then 3 thermostats. What are the loads on those circuits? Well, you see R1, R2, R3, R4. Those are relay coils. And they have switches that are addressed to them. You see an R1 normally open switch. Oh, and there's also an R1 normally closed switch. That's right over here. You see an R2 normally open switch, an R3, an R4, and the same thing up here on line voltage side. So what's the sequence of operation? Well, let's think about this. We get a call for space heating, so let's look at zone number 2. So here's my power. Here's a normally closed switch. There's my room thermostat that has to close. Here's my load, R2 relay. We energize it and we complete the circuit. Once I complete that circuit and energize one R2, my R2 normally open switch is going to close here, and we will bring power down to this relay coil here, which is a B relay coil, and that happens to be for the gas valve. And we complete that circuit. All right, so everybody see that. And also on the line voltage side, R2 switch normally open is going to close. So we're going to turn on the circulator. So the circulator will come on first. We energize the gas valve, and if it's a standing pilot, we're going to close the TT on the boiler. Woof, we make a fire. Okay, same thing will happen on zone 3. Same thing will happen on zone 4. Here's the cool part. Now you get a call for domestic hot water. The aquastat is going to close. Watch what happens. So the aquastat closes. Power, switch, load. I energize R1 relay, complete the circuit. By energizing R1 relay, R1 normally open switch on line voltage closes, circulator comes on immediately. But what else happens? R1 relay normally open switch here closes, and again, then we start energizing the B coil. We energize the gas valve, close the B normally open switch, and we would turn on the boiler. But something else important is going to happen. This normally closed R1 switch is going to open. So now if any of these thermostats call because it got cold in the room, it doesn't matter. This switch is open. No power can get down here. There's your domestic priority. So as long as the aquastat is closed, domestic rules, that's the only circulator that's going to run. Once the aquastat is satisfied and open, then the R1 normally closed switch goes from now an open position back to closed, and then we can send power to these zones when they're cooling. So gentlemen, there's domestic priority. We just took a normally closed switch and opened it and stopped power from going to any of the heating zones. Now here's another fancy relay put in a nice box with a lot of lights. You have to do some programming on here, and it's made by Tekmore. But all it is a relay. And let me show you. I'm going to expand this so you guys can see it better. All right, we're going to try to expand it. Here we go. And if we look right here at terminals 1 and 2, it says boil demand. And what do you see right there? That is the symbol for a relay coil. So if I put my thermostat or end switch from a zone valve or just a jumper across 1 and 2 terminal, I'm going to energize that relay coil. What's going to happen? Well, this boiler normally open switch on terminals 11 and 12, that's going to close. That's going to close the TT on the boiler. It's going to fire the boiler. And over here, here's your line voltage coming in, and what's connected to that on terminal number 7, boil P1. That's the boiler circulator. So I will close this normally open switch here on number 7, turn on the circulator, and fire the boiler. What do we have here across terminals 3 and 4? DHW, domestic hot water demand. And there's another symbol for a relay coil. So if you had an aquastat wired directly to here, or a thermistor, or you just put a jumper across terminals 3 and 4, I'm going to energize that coil. So now what's going to happen is the boiler TT will close, and now I'm going to energize the domestic hot water circulator. There's domestic priority. All right? Very simple, very easy. That's what we're doing here in this very sophisticated relay box. Okay? Over here, you can see we have dry contacts. No power is applied. This is where we're going to put some sensors. Here we've got a supply water sensor, a boiler sensor, the outdoor air sensor, and your indirect sensor. And you see the common terminals. So to complete those circuits, the sensor would get wired here and then go to COM. The sensor for the boiler would get wired here and go to COM. The outdoor sensor goes to out and goes to COM, and the indirect sensor goes to the indirect and COM. All right? Pretty simple stuff. Now I just got to get this to go back. Okay, here we go, guys. Sorry about that. All right, so here's a wiring diagram and a ladder diagram for a Weil-McLean boiler, and this happens to be standing pilot. So if you look over to the left-hand side, you will see the wiring schematic. It's showing you what is connected where, but it doesn't tell you the sequence of operation. Look over on the right-hand side, there's my ladder diagram, and it will explain the sequence of operation. So what is that sequence? Let's figure this out. Well, here's my line voltage, heavily drawn lines, service switch by others, that's the switch at the top of the stairs. Looks like it's drawn in a normally closed position. That's good, okay? And you can see on this rung there's a CR2 switch normally open and a circulator. Then we have our what? Our transformer. Here's our low voltage side. So here's my power. Let's look for our switch, which is our thermostat. And then we have a relay coil CR. That's my load, power switch and load. I complete that circuit. What happens to this CR relay coil once we energize it? There has to be switches addressed to it. Here's a CR1. That switch will close, and now power will come through and have to go through this limit switch, a spill switch, another limit switch, and a rollout switch, and then eventually go through a fuse to get to the vent damper motor. So gentlemen, these are normally closed switches wired in series, and they're safeties. If any of them open, we won't bring power to the vent damper motor. All right? So what happens here? Once we close the thermostat and we energize CR coil, CR1 will close, CR2 will close. So first thing you'll hear is the circulator is going to come on to establish flow. Once power starts going through all those normally closed switches, we energize the vent damper motor. You hear, vent damper motor opens, and when it does, it will close an end switch, which will then energize the gas valve. There's two more coils in there. We energize those coils. They open the gas valve. Since you see thermocouple, that's our standing pilot, woof, we make a fire. It's as simple as that. What if we did the same thing, spark igniter? Because now you can't buy anything with a standing pilot. So again, on the left, there's your wiring diagram telling you where things are connected, but on the right is the ladder diagram. So what's different here? Well, here, the spark module is on the line voltage and the low voltage side of the ladder diagram. But not much is different than the other operation. So here's our line voltage at the top, service switch, and this is drawn in a normally open position, so that better be closed, and that will complete that circuit up here. And there's our control module, and there's the circulator. Down here on the low voltage side, there's our transformer, there's my power. What's my switch? There's my thermostat. And as we go into the spark module, all right, it says T-stat circulator, and then it's also connected to the vent damper motor. So we're going to start energizing what? The circulator. It's the first thing that'll go on. And power has to then go through the rollout, the limit switch, a spill switch to energize now the vent damper motor. Vent damper motor is going to get energized and open. And what do you see right here? Damper end switch. So once it opens, it closes this switch, which then is going to energize our gas valve and also energize the spark box. So then you hear the click, 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 vroom, and the boiler fires. All right? So really no different than what you just saw. Excuse me. So now here, let's start talking about how we lay out our systems and how we want to control the different loads in our systems. So here's a zone valve system. This is 3 zones of space heating with 1 zone of domestic hot water. So here's my boiler, here's my air separator, expansion tank, my fill valve, here's my circulator pumping away. You know all about that stuff from our hydronic classes. If not, take them. And then here's my 3 zones of space heating and a zone of domestic hot water. Any one of these thermostats call will energize the zone valve. We'll end up turning on the circulator, and we will fire the boiler. If the aquastat calls here, we energize this zone valve, and we turn on that circulator, we fire the boiler. All right, so that circulator is going to run if any space heating or domestic calls. Okay. How would we wire that up? Well, to make life easy for you, Takeo does have our zone control relays for either zone valves or for pumps. This does make life easy. It takes a B tech in your company who maybe is a little sketchy on wiring and can really elevate them to an A tech when it comes to wiring, because this is very simple to set up. What are we going to do? Well, first off, we've got incoming power coming into this, and that's pretty obvious. All right, that's your red and orange wire there off to the side. That's incoming power. And then I got my thermostats wired to the top, and we have 3 terminals, R, W, and C. So if you've got a standard 2-wire stat, just goes to R and W. If you've got a digital stat that needs constant 24 volts, there's your common terminal, that would be C. Your priority zone is always the last zone, and that's where my aquastat will go to. Now, I got to prioritize that zone. We give you a switch right on the box, and we set it to open, or we set it to on. Pardon me, we set it to on. So that means we've got that normally closed switch sitting in that box, all right? So when priority calls, all right, that switch will open, and that'll cut power to your space heating zones. What else do we have? There's our isolated end switch, so we're going to take 2 wires out of there, and that will go to TT on the boiler. All right, so that's pretty simple. What's next? There's my relay coil, double pole, double throw, that will turn on and close the switches as needed right here at the bottom, because I have dry contacts here. Here I can drive up to 3 circulators. And then what's next? What's next is at the bottom where the zone valves are, and I give you 4 terminals. 1 and 2 is your motor, 3 and 4 are your end switch. So if you're talking Honeywell, 1 and 2 yellow, 3 and 4 red. If you're talking 571s, terminal 1 to 1, 2 to 2, 3 to 3. You're talking the Takeo Zone Century. We label 24 volts right on the zone valve head. That goes to 1 and 2. We label end switch. That goes to 3 and 4. The other neat thing is right here we have a series of lights. Right here is the top light, which would be green. So when this board is powered, you've got a green light. Every zone gets 2 lights. When there's a call for heat, we're going to have a yellow light up. And then when the zone valve is energized and the motor turns the valve open and closes its end switch, we'll light a red light. So that's a great troubleshooting tool. So if you're on the job and zone number 2 is not working, well, do I have power? If I got a green light, we've got power at the board, so we save you time there. Is the thermostat good? Well, yeah, we got a yellow light because the light's lit up, but the red light didn't light up. What's that telling you? There's something wrong with the zone valve motor. So you've really taken a lot of troubleshooting time and dramatically made it so much simpler for all your techs. So the wiring of it's so simple, and the troubleshooting makes it very simple. Now, what if I want to do the same system and I want to have domestic priority and I want to do 2 circulators? How do I wire this up, and what's my sequence of operation? All right, so instead of a zone valve for the indirect, I need a circulator because I need more flow than I can put through the zone valve. So how do we do this? Now this is where we take advantage of those dry contacts on the lower left-hand side of the ZVC panel. So we're going to bring power into this pump end switch. That's your black wire. We're going to come out of that pump end switch and go to common with a black wire. We're going to come out of normally closed switch to the system circulator with a black wire. And then out of normally closed, we're going to come out with a black wire and go to one side of the domestic circulator. What do you see here, gents? You see a dot? That's a wire nut. Then we have to take care of the neutral side, all right? And we also go from our isolated end switch at the top of the panel to the TT on the boiler. So what's going to happen here? How am I going to sequence these circulators? Well, the system circulator has to run when there's a call for heat. So we come into the pump end switch, and that is a normally open switch. This switch is set to normally open. And this switch will always close when anything on the panel calls for heat. So this switch will close all the time. So that means now power will come through, it'll come through the common, and you can see that it goes to this normally closed switch. This switch stays closed unless you have domestic priority energized. So now power will come through to my system circulator, and I complete my circuit. If domestic calls, well, normally closed switch here will now open, and the normally open switch will close. Remember, this switch will always close when there's a call for heat. So power will come in, go through the pump end switch, and then when it hits common, instead of going to the right to normally close, it'll go to normally open because it closed, and will energize our domestic hot water. I like to tell people that common is like the ramp off of a highway. You're driving on the highway, you get off of an exit ramp, and at least in New Jersey, you can either go right or left. You're either going to go over the highway or you're going to go to the right and away from the highway. So common is like your exit ramp. Power can go either to the right or to the left. So I'm sending power all the time to that normally closed switch, but if domestic priority calls, the normally closed switch will open and the normally open switch will close. So we cut power to the circulator that we don't want to run, and we only give power to the circulator that we do want to run. So you'll see the normally open pump end switch close, normally closed pump switch stays closed, we energize system 1, but domestic calls, now normally closed opens, normally open closes, and we energize the domestic circulator. Now if you do something like that on this panel, you have to put a jumper on terminal 3 and 4 of where you normally would have had a zone valve. And we make that very clear on the panel because when you take off the cover, inside the cover are the directions, and that is always printed there, besides in the printed directions that come with it. And what we're doing is artificially closing an end switch on the panel. We have to let the panel know that, yep, that switch is closed, and we've completed the circuit. Now, what if you do a primary-secondary system? Excuse me. Here, the way it's sequenced, I need to run 2 circulators for space heating. I need to run 2 circulators for domestic hot water. So what does that mean? Well, since this is primary secondary, and you've come to our hydronic classes, you learned what that is, and you know with closely spaced T's, the only way to induce flow here is to have this circulator come on and this circulator come on, because I've got flow constantly going through this loop. And then the only way to induce flow here is to turn this circulator on. Whatever flow it pulls through, the same amount goes back. So if I need space heating, we got to run 2 circulators. Domestic calls, I still got to run 2 circulators. Got to run the primary, and I've got to run the domestic, the only way to induce flow into the coil. So we have got to constantly run this circulator if anything on the system calls, and then we have to stagger or sequence when we want to run these 2 circulators. How are we going to do that? Well, we go back to our same pump relay, our ZVC system, and on the bottom we have those dry contacts. And the secondary circulator, that's my space heating circulator, is still going to be wired at normally closed. My domestic is going to be wired still at my normally open. Where will I put my primary? My primary, since it has to run anytime anything on the panel calls, is going to get wired to the pump end switch. Remember, the .UC is a wire nut. So that means the sequence of operation is there's a call for space heating, the pump end switch is going to close, the primary circulator runs, so we've got water going through the primary loop moving around, and we energize the secondary circulator, my space heating circulator. We get a call for domestic. The primary circulator is always going to run. Normally close will open, normally open will close, and we'll only send power now to the domestic circulator. So that's how we sequence these circulators. What if you did it and piped your system this way? We call this direct hot water because now when domestic hot water is calling, I only need to run 1 circulator. This circulator here is sized for the amount of flow rate I need through the coil and can overcome the pressure drop through the boiler. I don't have to turn this circulator on, and I need to keep this one off. But I still need to run these two circulators if we need space heating. So how do we sequence that? Well, again, the secondary circulator you see here, our space heating circulator, is still on normally closed. Domestic is still on normally open. But now the primary, where am I going to put that? Well, what if we wired it and connected it to normally closed, just like the secondary circulator? So that means when there's a call for space heating, the pump end switch will close, normally closed switch will stay closed, and I'll turn on now the secondary and the primary circulator. Okay, life is good. We get a domestic call, the pump end switch will close, but now my normally closed switch is going to open, my normally open switch is going to close. There is no power to primary and secondary circulators, only the domestic hot water circulator. It's pretty simple, pretty easy. So based on how you pipe out your system, that will dictate how you're going to sequence your circulators. We have the same type of relay panel for multiple pumps, because not everybody will do their systems with zone valves. So we have the same thing for multiple pumps. This is called an SR relay. Here I'm showing you a 4-zone switching relay, so a little bit different than the zone valve one. I do have the green light for power, and then each zone gets its own light. And when we energize the thermostat, or the thermostat energizes the system actually by closing, each zone light will light up. Pardon me, each zone light will light up. So you'll see a red light there. And then we would be turning on that circulator. So at the top is where my thermostats get wired in. The last zone is always the priority zone, and there's my switch to either energize it, to turn priority on or turn it off. Here's my isolated end switch. This is what's going to close the TT on the boiler to start the next series of power, switch, and load. On the bottom is where my incoming power comes in, and here's where I can wire in all my circulators. You do see this jumper across ZC and ZR. That enables us to do other things with this panel. If I wanted to hook it up to another relay switch and have that switch control it and say add outdoor reset to this type of switching relay panel. All right, so Aquastat is going to go to priority zone 4, and I put my circulator on zone 4 for that domestic priority. So here's a wiring layout for an SR504 or 506, and I'm going to my standard L8148E boiler control. So we're going to bring incoming power from the circuit panel through all those different switches. And I want you to pay attention from the circuit breaker, then the customer emergency switch, maybe there's a thermal fuse on there, the service switch. So your customer emergency switch is where? Top of the stairs. Service switch at the boiler. Low water cutoff, well, in this instance, it's in the line voltage side. That's 120 volt low water cutoff. That means if the probe gets fouled and it now can't receive its signal and it goes from a normally closed switch to normally open, we cut power to this whole system. Nothing's going to run. So if the system's been running fine, now you get a call, now it's like nothing runs. There's nothing. And you show up and you don't see power at the board, check your low water cutoff. It could have a dirty probe, and that's what opened that switch, and that's what cut power to the board. So we're bringing power in, and we got to bring power to the boiler too. So what do we have next? We have another wire nut bringing power to L1. All right, we complete the neutral at L2. We got to do the same thing to the boiler. So there's our incoming power. What's next? Thermostats, thermostats, thermostats. What's next? Pumps on the bottom. And what's next? Isolated end switch to TT on the boiler. Can't make it any simpler than that, guys. Very simple, very easy. Again, your B-Tech can now wire up this system. You don't have to worry about bringing an electrician to do this. Just have power that you can connect to the board. Here's the same thing for a ZVC. This is for a zone valve in either a 4-zone or 6-zone system. I got domestic hot water here, okay, and some secondary pumps. So take a look and see how we do this. Again, power to the board the exact same way. Again, there's a low water cutoff in the line voltage, so that's a 120 low water cutoff. And we bring power to one side of the transformers. To finish that, L2, we bring, that's your white wire, to the other side of the transformers. You see the two dots, those are wire nuts. Now the way this is drawn, the transformers for this ZVC panel are outside the panel, but in reality they're inside the box. And why do we have two transformers? We have two transformers because the box is cut in half. So one transformer on this 6 zone is taking care of zone 1, 2, and 3. The second transformer is taking care of the next 3 zones, 4, 5, and 6. So what do we have next? We're going to wire in our thermostats and or aquastat. All right. Again, we give you 3 terminals, so if any of those are digital thermostats, you got your C for common for your 24 volts. What's next? Well, let's bring in our zone valves. Now, this is really cool. I give you 4 terminals. So whether you have a 2-wire with no end switch, the Tekmore 3-terminal 571, or whether you have anybody's 4-wire zone valve, and I'm going to be talking here about Zone Sentry, we can wire them all up on the same panel at the same time. So if you've got any 2-wire type of zone valve or actuator, you're going to take power off of 1 and 2. But since there's no end switch, you got to put a jumper across terminal 3 and 4. The Tekmore 571 is so simple. Terminal 1 to 1, 2 to 2, 3 to 3, done. Anybody's 4-wire, well, your 2 yellows would go to 1 and 2, that's power, and 3 and 4 would be the end switch. That's the Tekmore Zone Sentry. We label on the valve motor itself 24 volts, so that's going to go to terminal 1 and 2, and end switch would go to 3 and 4. You would use standard thermostat wire to wire that up. That valve does not come with wires. So standard thermostat wire. So then what do we have here? Well, we're going to take our isolated end switch, right, to go to TT on the boiler. Then what's next? I bring power into my dry contacts on the lower left-hand side there, all right? So we're bringing a black wire down into pump end switch. We come out of that pump end switch with another wire that goes to COM, and then we continue also the system pump. We take another black wire out of normally open to the domestic pump. We take another black wire out of normally closed. That goes to the secondary pump. And then we have to, that's just the power side. We have to complete the neutral side, right? And then we take our white wires from one side of each one of those circulators back up to the incoming power. So now if any thermostat calls, we're going to get that light for that particular zone to light up. Once the zone valve is energized and open, we'll get that zone's red light to come on. That shows you that the end switch made. Since we're going to take the system pump is wired here. That pump end switch closes, so that system pump will come on. Secondary circulator will come on because that normally closed switch stays closed. So now I'm running those 2 circulators. If the aquastat call for domestic priority, we still close the system pump, but the secondary pump won't get any power because that's going to open, and the normally closed switch for the domestic pump will close, and that circulator will get power. Here's how we wire up multiple switching relays together, and when we do that, these are our EXPs, that's expandable, and we have them for pumps and we have them for zone valves. So a couple of different features, but everything else is exactly the same. So incoming power, just like you're used to doing, all right? So they're going to share both incoming power. Thermostats and aquastats get wired to their respective panels. Same thing for our circulators, since this is an SR panel. Now, what's different? There's an expansion block on each panel. So one of these panels has to be labeled as the master. So you can see on the left-hand side of the panel, and let me see if I can make this bigger for you. Right here, you can see those dip switches, and you can see slave and master. So if master panel is going to be the one that will do all the communication back to the boiler. So that dip switch has to be set to master. If you're going to have priority, either on or off on that particular panel. You set the dip switch to its proper place. Then it says reset and normal. If you don't have outdoor reset connected to this panel, which would be where it says power controls, that's a Molex plug, we would just plug in our outdoor reset control, our PC701, then you would just leave the dip switch to normal. Then unless you want to use the primary pump on or post purge or priority protection that is, or the pump exercise or low limit ZC on, you can keep those to off. If you want to use any of those extra features, you would just slip them to the on position. Okay? So let's get back. Excuse me here, gentlemen. This just gets a little tricky for some reason. And then the other box you'd have to set to the slave position. And then we continue with A to A, B to B. We can get that to go back. Here we go. So now A to A, B to B, C to C. Now the two boxes will talk to each other, but all communication back to the boiler goes through master. So we have your end switch going to TT on the boiler, but since these are expandable panels, we give you another end switch. That's your priority end switch. That's for domestic hot water. A lot of condensing boilers have two TTs on them, one for space heating, one for domestic. So we make it that you have two isolated end switches on these panels to make that wiring simple. Okay? I mean, can't make this any easier. And you have the ability to expand these out to 120 zones. So you do have the ability to take on some pretty big projects and wire it up pretty simple, pretty easy. Okay? And then we give the priority pump if you need to wire it to the panel. All right. So if you want more information or if you have questions, how can you get a hold of me or how can you get a hold of anybody else in the contractor services group at Wales-Darby? Well, you can email me at jdepalm@walesdarby.com or you can call us at 732-560-1001, ask for technical support, and they will switch you to anybody in contractor services. The file link that you see up there, that's to the TACO library. That's how you can get the TACO wiring diagram. Highly recommend you do that. You can download it to your computer, then you can print it if you choose, or if you want to request one from us, we'll mail one to you. And that will show you all the different wiring options that you can do with our SR single zone or SR multi or ZVC multi panels. All right, we can do a lot of different things with these controls. That's how you can get that information. And also on the bottom, I'm referencing two books by the author Carol Fay. This whole presentation was based off of her two books, Quick and Basic Electricity and Quick and Basic Troubleshooting. Carol Fay was a tech at Honeywell for like 25 years. Brilliant woman, and she does a lot of great podcasts on just basic electricity or electricity in general, and these two books are excellent. They're great books. I think they'll cost you maybe $20, and they'll take you under an hour per book to go through, and that will reinforce everything we went over today. Great reference material. Everybody in your company should spend some time going through that. It would help tremendously. Because again, what we see is most contractors can pipe up, but then when it comes to sequence of operation, they're not 100% sure. And if we can understand the sequence of operation by understanding the ladder diagrams, which every piece of equipment comes with, you'll be able to understand the sequence and set up your systems the way you want them to work, and it'll really help you in troubleshooting anything. And it'll help you when you're talking to tech support in any of these companies. You'll be able to understand or explain to him what's happening. He'll understand you and be able to explain back to you what your troubleshooting method would be. All right? So please contact us with any questions. Please check our website for more of these webinars. There's plenty of them. And I thank you very much for coming today.